First of all, let me welcome you to this, give you my welcome to this summer school. We're going to be talking about combustion chemistry. And let me say a little bit about me, first of all. I come from the University of Leeds in the United Kingdom, and that's the position of Leeds in the north of England. So England goes up to about here, and then we have Scotland, and Leeds is up in the north of England. And I live in a small town called Ilkley, which is about 20 miles north of Leeds, surrounded by moorland, what we call moorland, which are these rolling hills. They're beautiful hills to run on, and also rock climbing is very common in our area. Notice also this is a beautiful day by Leeds standards. Usually the rain is coming down, as signified by these rather grey clouds here, but this particular day was nice. One of the things about this course is that it's chemistry, it's chemical kinetics. I suspect that many of you are engineers. Maybe we ought to take a poll. How many of you in your first degree were engineers? And how many of you were chemists? So some, but not many. And how many physicists, mathematicians? Okay, so not a lot of you were chemists or are chemists. But this is going to be unashamedly chemistry that we're talking about, because we feel that chemistry is important in combustion, and that engineers as well as chemists need to understand chemistry and in particular chemical kinetics, because it's so central to combustion processes. One of the results of this is that some of the things I say may not be absolutely obvious to you, and I may not be as clear as I should be. So if that's the case, do please raise your hand, and I'll try and explain it. Do more than raise your hand, yell out, and I'll try and explain what's going on. And what we'll do is we'll try and stop periodically, and I'll take questions. And so if you have questions that you think may take a little bit more time explaining, then maybe that's the time to leave them to. But if things are not clear, or especially if I make mistakes, then do please yell out. Okay, so let's look at a little bit of background. So combustion involves the oxidation of a fuel, and if it's an organic fuel, such as octane or ethanol, then it leads in the end, and one hopes completely, to the formation of carbon dioxide and water, and importantly with the release of heat. The overall chemical reaction could be written like this, with, in this case, ethanol reacting with oxygen forms CO2 and water. But this doesn't describe in any way how the reaction itself occurs. And the reaction occurs by a sequence of steps. The overall reaction occurs by a sequence of steps involving what we call elementary or single-step reactions. And these elementary and single-step reactions involve atoms or radicals. And so these are highly reactive species, which often react on very, very short timescales. So they're short-lived, and they have high reaction rates under the conditions that we would be looking at. So what we'll do in this series of lectures is examine how the rates of these elementary reactions can be determined both experimentally and theoretically. And as I hope will be clear, it's important that we have both experiment and theory working together to help us understand these reactions so that we can then use them in models for combustion. So then what we can do is we can construct chemical mechanisms which consist of sequences of these elementary reactions that can be used to model the overall chemistry. So we have these two stages, the elementary reactions, which we need to understand, and with that understanding, we can then construct chemical mechanisms, and we can put them in models of combustion processes. So here's an example. So this is the hydrogen-oxygen reaction, one of the simplest combustion systems, and a minimal set of reactions could be of this sort. And I'll discuss this in a little bit more detail later on, but I'll use some of these reactions as examples of some of the issues that I want to discuss over the next few minutes. So hydrogen and oxygen molecules react together to form two radicals, or an atom, H, and a radical, HO2. The point about radicals is that they have a spare odd electron, and that odd electron wants to combine with other molecules to form a stable molecule. Other molecules or radicals to form a stable molecule. Then this hydrogen atom can react with O2 to form the hydroxyl radical, OH plus O. O can react with H2 to form OH plus H. OH reacts with H2 to form H plus water. And then this is an interesting reaction here where H plus O2 can not only react under these conditions here, forming OH plus O, it can also react to form HO2, this radical that was initially formed up here. So H plus O2 can react to form HO2. And there's an M in there. M is what's called a third body. So typically in a combustion system, it would be oxygen or nitrogen acting not reactively, but simply as a means of taking energy away from this system. So when H plus O2 react together, they carry with them energy which would cause this HO2 to dissociate unless it were thermalized by collision with this third body M, with oxygen or nitrogen, or maybe water. And we'll talk a little bit more about the way in which this sort of reaction occurs. Then, especially at low pressures, what can happen is that the reactive species, HOOH, can diffuse to the wall. So before they encounter a reactive species, they can diffuse to the wall and react at the wall. So they'll be removed from the chemical system by reacting at the wall. And then finally, a reaction HO2 plus HO2 reacting together to form hydrogen peroxide plus oxygen. And so that's a minimal set of reactions, but it's quite a useful set of reactions to understand the way in which this overall combustion system operates. So let's have a look at rates of elementary reactions and just have some definitions. So periodically, what you'll find is one of these yellow stars, and I've put the yellow stars in after revising the lectures and where I found errors. So at this point, what I've written down is going to differ slightly from what you've got in your notes. So you need to put in some corrections. Okay, the rate of each elementary reaction is determined by the reactant concentrations and a constant called the rate coefficient. K depends, and we give that rate coefficient a symbol K. And K depends on temperature and in some cases on pressure. We also need to know the products of the reaction, which in some cases aren't clear. So for example, that reaction that I showed you earlier, H plus O2, can react to form OH plus O, but it can also react to form HO2. And we need to know the relative rates of those two reactions. But just let's concentrate first of all on this reaction, H plus O2 going to OH plus O, and we'll give it a rate coefficient K2. And the rate of this reaction we can write down as minus DOH by dt, And that's equal to the rate coefficient multiplied by the concentrations of the reactive species. And that leads to the formation of products, and the rate of forming the products is dH by dt or dO by dt, and this is where I made an error in the original slide, so if you could correct that. And dH by dt and dO by dt necessarily must be equal to minus dOH by dt, and therefore to K2 times H times O2. K2 depends on temperature, and this is usually expressed in what's called an Arrhenius form, which is A times the exponential of minus EA over RT, or in modified Arrhenius form, where K2 is equal to A T to the N times e to the minus EA over RT.
Professor?
Yes?
Should DO be negative if DOH is negative?
No, dO by dt is positive. So what's happening is H is reacting with O2. Yes, okay, so there is yet another error there. That should be, sorry, let's write this out properly. Thank you very much. I think I had another reaction in there to begin with. So what we should have is minus dH by dt is equal to K2 times H times O2. Okay, that much is right, which should be equal to plus dO by dt and plus, and that should be equal to plus dOH by dt. Okay, sorry about that. Does everybody agree? Okay. So I managed in the star to get it wrong still. So I'll correct that. What we'll do is produce a final set of lecture notes which will be mounted on the web, and those should be a definitive set with the proper corrections in. Okay, so let's go through this again, because some of you were quite rightly thinking whilst I was going through it. K2 can be expressed in Arrhenius form or in modified Arrhenius form, where A is the A factor, EA is called the activation energy, and N is the temperature exponent, and R is the gas constant. So one aim of experimental and theoretical studies of elementary reactions is to determine A, EA, and N. Just let me quickly tell you about a couple of issues that you need to know about, which are the orders of reaction and also the units of the rate coefficients. So if we look at this reaction that we've been talking about there, where we've got dH by dt minus, which is the rate of the reaction, and we'll call that rate of reaction nu. That's equal to K2 times H times O2. And the order of reaction is the power to which these concentrations are raised. So this particular reaction is first order in H, and it's also first order in O2. And the overall order is given by the sum of those orders. So this particular reaction the overall order is second. It's a second order reaction overall. Can you read that? Is it large enough to read at the back? Let's have a look at another example, which raises another important issue. Let's take HO2 plus HO2 going to H2O2 plus O2. And the rate of this reaction is equal to the rate constant, which is K7 multiplied by HO2 squared, because there are two HO2s involved there. We also have a factor of 2 in there, as far, if we define the rate as being minus d HO2 by dt, then we have a factor of 2 in there to define the rate coefficient. And that's purely a convention. But if you go through combustion mechanisms, then you'll find those factors of 2 in there for reactions of this sort. So dHO2 by dt is going to be twice K7 times HO2, and that's going to be equal to plus dH2O2 by dt. That's going to be equal to twice dH2O2 by dt. Okay, so that factor of 2 in there is purely a convention, but it's a convention which is observed throughout kinetics. And this reaction is second order in HO2, and it's second order overall. So the rationale for these orders will become clear when we talk about theory tomorrow, but one simple way of thinking about it is that for this reaction to occur, H has got to collide with O2, and the rate of those collisions will depend upon the concentration of H and on the concentration of O2. For the second reaction, HO2 has got to react with HO2, and so the concentration is going to, the rate of those collisions is going to depend upon the concentration of HO2 and the concentration of HO2, in other words, the concentration of HO2 squared. And these rate equations simply depend upon the concentrations of the reactants. They're independent of the concentrations of the products. They just depend upon the concentrations of the reactants. Okay, just let me say something about units. If we look at units, if we look at the units of nu, which is the rate of reaction, that's going to have units of molecules per centimeter cubed per second. So it's going to have units of concentration per second. So for example, that's equal to minus dH by dt. So the units of that are concentration per second. Often these are given in molar units, and so then the concentrations are moles per centimeter cubed per second. I'm going to tend to use molecular units, but molar units are very widely used in combustion mechanisms. So you need to be aware of these two and aware of how you convert from one to the other. And so going from here to here, we have to multiply by 6 times 10 to the 23, or if you're being accurate, 6.023 times 10 to the 23, going from molecules to moles. So that's multiplying by what's called the Avogadro number, Na. So the rate is going to be much larger. We're going to need to divide by that in order to go from rate in units like this to rate in units like that. So if we're then going to look at the rate coefficients, then for a second order reaction, a reaction which is second order overall, then the units of the rate coefficients are going to be centimeters cubed per molecule per second, molecule per second, or centimeters cubed per mole per second. And to go from here to here, you need to multiply now by 6.023 times 10 to the 23. So the units of a second order reaction are much larger in molar units than in molecular units, numerically larger. If we're taking a first order reaction, then the units are seconds to the minus 1. And you can work those out easily just by going through the relevant equations. So it's important to know what these units are and to know about the interconversion between molecular and molar units. Okay, another important quantity we need to understand is the equilibrium constant. And here are some definitions of equilibrium constants. And so, for example, we might have this reaction, hydrogen plus O2 going to H plus HO2, and its reverse reaction. And so the equilibrium constant, and this is what's called a thermodynamic equilibrium constant, is equal to the product of the activities of the products raised to a stoichiometric coefficient mu I divided by the product for the reactants of these activities raised to this exponent mu I, where A is called the activity. And for an ideal system, the activity is the pressure divided by the standard pressure, which is 1 bar, or the concentration divided by the standard concentration. And that could be, for example, 1 mole per centimeter cubed. K is dimensionless because these activities are dimensionless. Other definitions of equilibrium constants that you come across are the equilibrium constant in terms of concentrations, where we have the same sort of expression, but now in terms of concentrations rather than activities, and an equilibrium constant in terms of partial pressures, where we have we've basically got the pressures instead of the activities. And these will have dimensions if the sums of these stoichiometric coefficients for the reactants are different from the sums of the stoichiometric coefficients for the products. Now, I'd better do a bit of explanation here because the notation, I've managed to confuse the notation. Here, I'm not talking about rates here, I'm talking about stoichiometric coefficients. So let's define what these stoichiometric coefficients are. So for example, if we had H2 plus O2 going reversibly to H plus HO2, then the news, where these are now the stoichiometric coefficients, they're all unity. So there's 1H plus 1O2 going to 1H plus 1HO2. And so the equilibrium constant now is simply equal to the activity of H times the activity of HO2 divided by the activity of H2 times the activity of O2. If, on the other hand, we had the reaction 2HO2 going to H2O2 plus O2, then the equilibrium constant now would be equal to the activity of H2O2 times the activity of O2 divided by the activity of HO2 squared. So when we're constructing these equilibrium constants, then we've got to recognize the importance of these stoichiometric coefficients. To give you another example, let's take this reaction. C2H5 goes reversibly to H plus C2H4. And let's have a look at the equilibrium constant Kc. So this is the equilibrium constant in terms of concentrations. Then this is going to be equal to the concentration of H multiplied by the concentration of C2H4 divided by the concentration of C2H5. And so that's going to have units. It's going to have units of, say, moles per centimeter cubed. So the equilibrium constant Kc, written in terms of concentrations, is going to have units in this reaction because the sum of the stoichiometric coefficients for the reactants is equal to 1, and that sum for the products is equal to 2. So that's a situation where these equilibrium constants will have dimensions because these sums of stoichiometric coefficients are not equal. So I apologize for the confusion between the symbol I used for rates and the symbol I used for stoichiometric coefficients. But I hope it's pretty obvious what the differences are. Now, at equilibrium, necessarily, the rates of the forward reactions will be equal to the rate of the reverse reaction. Because otherwise, we won't be at equilibrium. And that's a definition of equilibrium that it's what's called a dynamic equilibrium, where the rate of the forward reaction is equal to the rate of the reverse reaction. And so if we take the rate of reaction, these are elementary reactions, so the rate of the forward reaction is going to be equal to there's the rate of the forward reaction, Kf times the product of the concentrations of the reactants, of the products raised to the power nu I. Sorry, I've got this wrong as well. So this is the rate of the forward reaction, which is equal to Kf times the sum over the reactants of Ci to the nu I. So that should be reactants there. And that's equal to Kr times the product over the products of the Ci to the nu I for the products. And if we take the ratios of those, then that's Kf over Kr is going to be equal to Kc. So because of the confusion of my error, let's write that out in detail for a given example. So let's take that example we had originally. H2 plus O2 goes to H plus HO2. So the rate of the forward reaction is going to be equal to the forward rate coefficient multiplied by the concentration of H2 times the concentration of O2. And those are going to be the concentrations at equilibrium. The rate of the reverse reaction is equal to K reverse multiplied by the concentrations of H and HO2, again at equilibrium. So from that, what you can see, so these are going to be equal at equilibrium. And so we can say then that Kf over Kr is going to be equal to the concentration of H times the concentration of HO2 divided by the concentration of H2 times the concentration of O2, and this is all going to be at equilibrium. And that is simply equal to the equilibrium constant Kc. It's also equal to the thermodynamic equilibrium constant K, because the numbers of species on both sides of the reaction are the same. And so you can see from this that Kf over Kr is equal to Kc. And so if we know Kc and we know Kf, so if we know these two, then we can calculate Kr. And those of you who use Chemkin will know that the thermodynamic database is an essential element of Chemkin. And it's there because when you put in a forward rate coefficient, it automatically calculates the reverse rate coefficient. And it does that through an analysis of this sort. Okay? So we'll talk about thermodynamics on Wednesday in more detail, but the key thing is that if we have thermodynamic data and we know the rate coefficient in one direction, then we can find the rate coefficient in another direction. We'll talk today about ways of measuring rate coefficients, and knowledge of the equilibrium constant is important in terms of making sure that if we've got the forward rate coefficient when we're measuring the rate coefficient, our measurements are accurate. So we can use it in those contexts. So this slide in combustion is a really very important slide because of the relationship between thermodynamics and kinetics. So let's go a little bit further with that. So thermodynamic relations, more details on Wednesday. Constant temperature and pressure, the Gibbs energy G, or a change in the Gibbs energy is given by this relationship. Delta G is equal to delta H minus T delta S. And the equilibrium constant is related to delta G by this equation, which again has got an error in it. I'm sorry. That minus sign there shouldn't be there. That should be RT log K is equal to minus delta G. And so if we know the equilibrium constant can be calculated from tabulated values of enthalpy and entropy. We'll go through these tabulations on Wednesday. And hence the reverse rate coefficient, say, can be determined from the forward rate coefficient and the equilibrium constant. And that's, again, a slight change in wording from what you had in your original set of notes. OK, let's have a quick break. Any questions? Does anybody have any questions on what we've said so far? It's reasonably straightforward. most of you, I'm sure, know all of this stuff. But at least it's there as a reminder. Okay? And I apologize for the errors. Okay? So no questions. Sorry? The error on this slide, well, there wasn't an error. What I've done is slightly change the wording. Yeah, but there was an error in that minus sign. Shouldn't be there. Okay, let's now move on to the way in which we construct equations and reactions and mechanisms. So the next slide is constructing coupled differential rate equations from chemical mechanisms. Now, I apologize that this is small, but it's what we had a few slides before. So the chemical mechanism is set up with the associated rate coefficient. So what you do is you write down all of the reactions that you think are important, and with each of them, you associate a rate coefficient. And we'll talk about how those rate coefficients are measured later on. The coupled rate equations are then written down for each species. So the rate, so dx by dt, any species x, dx by dt, is the total rate of forming x minus the total rate of removing x. And so if we take h, dH by dt is equal to, it's formed in reaction 1, so K1 times H2 times O2. It's removed in reaction 2, so minus K2 times H times O2. It's formed in reaction 3, so plus K3 times O times H2. It's formed in reaction 4, plus K4 OH times H2. It's removed in reaction 5, minus K5 times H times O2 times M, this concentration of the third body. And then it's removed in reaction 6, minus K6 times H. It's not involved at all in reaction 7. Okay, so that's the total ordinary differential equation that describes the time dependence of the hydrogen atom concentration. And we can do the same for all the other species that are involved, both radicals and stable molecules. Another example there, which you can go through at your leisure, is DO by dt. And so we set those up for any, and then we solve the coupled differential equations numerically, subject to a set of initial conditions. And subject, of course, to the temperature of the vessel, or the temperature, depending upon the conditions, could be a variable of the process. Now, so that's how we set up the equations. Quite a useful thing to be able to do is to apply something called the quasi-steady state approximation. And let's go through what the QSSA is. So it's sometimes used to simplify, let's omit that I there, to simplify kinetic problems. So let's have a look at this scheme. A goes to B goes to C. And let's assume that there are rate coefficients K1 and K2. And we'll simplify the algebra by saying that the concentration of A is equal to little a, etc. So dA by dt is minus K1A. dB by dt is K1A minus K2B. We don't need to worry about C because we can get its concentration by mass balance. So the total amount of A plus B plus C is going to be equal to the initial concentration of A naught. Initial concentration of A, i.e. A naught. So those are the two differential equations we need in order to describe this system, and then use mass balance to get the amount of C. So A is going to be equal to A naught times e to the minus k1t. And if we solve for B, we get this expression here, A naught times k1 divided by k2 minus k1 times the exponential of minus k1t minus the exponential of minus k2t. And then C by mass balance. Okay. QSSA continued. So let's first of all look at a situation where K1 is greater than K2. So there is the scheme in small. Can you read that? Well, but it's basically A goes to B goes to C, K1, K2. This is the reactant. This is the intermediate. Those are the products. And we're going to start off with a situation where K1 is larger than K2. So what's going to happen then? Well, A is going to decay exponentially with a rate coefficient, with an exponential decay with a time constant, with a constant K1 in it. So it's going to decay as this term here, e to the minus K1t. And on that same time scale, B is going to build up. So this is minus an exponentially decaying function. So B is now building up with this exponential dependence here. And then, in addition, there is this slower decay, e to the minus K2t. It's slower because K2 is smaller than K1. And so what we see is A decaying, B building up, decaying away, and C coming in to reflect that decay of B. So A is forming B is forming C. The initial reaction occurs relatively quickly. B builds up to quite a high concentration and then decays away, and then C comes in. Now, figure B, let's look at the reverse with K2 now greater than K1. So here's our original expression up here. And what we have to do now, since K2 is greater than K1, we have to invert this bottom and therefore invert these two terms here. So we get A naught K1, K2 minus K1, e to the minus K1t minus e to the minus K2t. And so interestingly now, the buildup of B is determined by the rate coefficient which describes its removal, which is an interesting point. And then it decays away, and it decays away with the same time constant as A, e to the minus K1t. So there's the decay term, here's the production term. And C builds up, and it starts to build up even on this short time scale, and it's certainly building up to reflect the decay of A. And these are two different curves, the dotted and the full, which refer to K2 equal to 5K1, and then K2 equal to 50 times K1. Let's have a look at this one. K2 is equal to 50 times K1. What happens now is that B doesn't build up to a large concentration at all. It always remains very, very small. And through most of its lifetime, it's decaying at with the same time constant as is A. Okay, so A is decaying away, and B is decaying away, but its concentration is very small, and C is building up. If we take that equation now, this term here, we can pretty well neglect after a small initial, especially under these conditions, with K2 equal to 50 times K1, we can neglect this buildup. If we move beyond this buildup, then in this region here, we can neglect this e to the minus K2t term, and we simply get that B is equal to A naught times K1 over K2 times e to the minus k1t. And we can substitute a naught e to the minus k1t for a. Go back a slide, then you'll find that that's the case. So b is equal to a times k1 over k2. K1 is very much less than K2, so B is very much smaller than is A. And to a very, very good approximation, dB by dt, well, certainly dB by dt is very much less than dA by dt, and to a very good approximation, we can set it equal to 0. So that's a steady state approximation. We set dB by dt approximately equal to 0, which means that the rate of forming B is equal to the rate of removing it. And that's used very extensively in chemical kinetics of combustion system. And it applies when these sorts of conditions are there, where the species that we're interested in, B, is very short-lived. It reacts very quickly. Its rate constant for reaction is very high. And so it never builds up to high concentrations. And so to a good approximation, well, certainly dB by dt is very small, and to a good approximation, it's equal to 0. Another small definition. What we said was that A was equal to A naught times the exponential minus K1 times T. And so let's define a couple of time scales. We'll define a quantity tau, which is the time to decay to A naught over E. And tau is simply equal to is equal to 1 over K1. So the reciprocal of the rate coefficient, the first order rate coefficient, is equal to this time scale, the time for A to decay to 1 over E of its initial concentration. And that's a very, very useful quantity to bear in mind. If you're thinking about combustion systems, and you're looking at a particular species, how long is it going to hang around once it's produced? This equation will give you that sort of information. We can also define the half-life, which is the time to decay to A naught over 2. And if we give that the symbol T1/2, then that's equal to log 2 over K1. And an interesting feature of first-order reactions, these are all first-order reactions we're talking about. An interesting thing about first-order reactions is that T1/2 and also tau are independent of time. And that means that the first half-life is the same as the second half-life, is the same as the third half-life, etc., etc., etc. So and that's an obvious result of the exponential nature of the decay of A. So the half-lives are independent of time and independent of the initial concentration. They're independent of time and also independent of the initial concentration. Okay, let's move on. Pressure-dependent association reactions. We talked about that reaction, HO2 plus HO2 going to H2O2 plus O2. Sorry, yes, we talked about H plus O2 plus M going to HO2. So if we look at reactions of this sort, A plus B forming a product AB, then the way in which the reaction occurs is that it initially forms an energized adduct AB. Under these conditions, it's a conservative system, and the energy of AB star is going to be the same as the total energy of A plus B. And it will just go back again to reform the reactants unless a third body removes at least some of this energy to form this stabilized AB molecule. What you can do is you can apply the steady state approximation to AB star, which means that its rate of formation is equal to its rate of removal. And there's a little exercise for you to do in the vast amounts of time you have available to you. If we apply the steady state approximation to this, we can describe an overall rate coefficient which is equal to Ka times Ks times the concentration of M over K minus A plus Ks times the concentration of M. And examples include CH3 plus CH3 going to C2H6, and a reaction we'll talk about later, OH plus C2H4 going to C2H4OH. Now, if we take this expression here, you can see that as M goes to infinity, this term dominates at the bottom, so we can neglect the K minus A. And what that means is that all the AB stars are being stabilized, and so we neglect this term here, the KSMs cancel out, and K is equal to Ka. So every AB star that's formed with a rate coefficient Ka is stabilized. On the other hand, if we approach zero pressure, we can now begin to neglect this term here. So the rate coefficient becomes equal to Ka times Ks times M over K minus A. And we give that the symbol K0 times M. In the literature, there's some differences of definition here, and sometimes this overall expression here is called K0. But I call it, in what follows, I've referred to this as K0 times M. And if we look at the time dependence of that, the pressure dependence of the rate coefficient. So if you plot the rate coefficient versus M, it looks something like that, where this asymptote here is K infinity, and the slope down here is equal to K0. So that's what the rate coefficient looks like as a function of pressure. Okay, now let's go back to our original mechanism and have a look at some of the characteristics of those component reactions. So this was the minimal set. And what I've done now is I've put labels next to the different reactions. Okay? I, B, P, T, and T. And these refer to the different types of reaction. I stands for initiation, B for branching, P for propagation, T for termination. And let's see what that means. The initiation reaction involves reaction of stable species producing radicals. So on this side of the reaction, we have no radicals. On this side of the reaction, we have radicals. And since radicals react quickly, they determine the overall, they're central to the rate of the overall mechanism. And so this initiation process is key because it's the one that generates the radicals. Then let's have a look at P. P down here is a propagation reaction. We've got one radical reacting with a molecule, producing a radical plus a molecule. So in this case, we've preserved the numbers of radicals on both sides of the equation, of the chemical equation. So the numbers of radicals in the reactants is the same as the number of radicals in the products. And so that sort of reaction sustains the rate of reaction because we're not removing the radicals from the system, we're simply regenerating them in the reaction process. And then the B's. These are the branching steps. H plus O2 reacts to form OH plus O. One radical produces two. O plus H2 forms OH plus H. One radical produces two. And so the result of that is that the reactive system, given the importance of the radicals in determining the rate at which the overall reaction occurs, the rate at which heat is generated, that sort of process, a branching process, leads to an autoacceleration. So the rate of reaction accelerates as we increase the number of radicals in the system because of these branching processes. And then finally, the T's. The T's, we have radicals on this side and no radicals on this side here. And at low temperatures, this species HO2 is very unreactive. What it does is it forms H2O2 here. And so this here is essentially a termination step because HO2 with this mechanism is going to do nothing other than form H2O2. And so that's the nature of these different types of reactions: initiation, branching, propagation, termination. Now, reaction kinetics contributions to combustion models. So what we've done so far is we've talked about reactions, rate coefficients, chemical mechanisms. How does this fit in to combustion? And this is a slide that tries to illustrate that. What we have is chemical kinetics, laboratory experiments, and theory. And these produce rate coefficients. And those rate coefficients then undergo something called an evaluation. Wise people look at those rate coefficients and decide what rate coefficients to recommend. And we'll discuss this on Wednesday. And using those, we can then construct a chemical mechanism. And we can then use that chemical mechanism, we can test that chemical mechanism with a macroscopic system such as a flow reactor. So I'm sure you've seen Fred Dreyer's, in the lab tours, you'll have seen Fred Dreyer's flow reactor. We can test this chemical mechanism in that flow reactor and see whether it works or not. We can evaluate the mechanism. And we will almost certainly find out that there are deficiencies in that chemical mechanism. And so we can go back to the lab and look at the rate coefficients where we think there are problems. And then what we can do is we can finish up with this, this detailed chemical mechanism which has been evaluated in detail, and the rate coefficients are the best that we think we can get. Now, those of you who are fluid dynamicists will know, and fluid dynamicists using chemical mechanisms will know that this sort of complete large chemical mechanism is far too large to put into a CFD code. And so what you have to do is to reduce or lump the chemical mechanism. We'll say a little bit, not very much, a little bit about this later on. You then introduce this into a complex model, which includes the fluid dynamics, and then apply that in combustion systems. So this slide is a way of illustrating the way in which what we're discussing, which is going to be this region up here primarily, how it fits into the complex models which are used to model an engine or a combustor of some sort. And the whole overall process also allows us to understand what's going on. Understanding is important in all of this. We shouldn't just have a mechanism that we use willy-nilly. We need to understand it. And the chemical kinetics allows us to understand that. And there are similar approaches in atmospheric chemistry. My other area of interest is atmospheric chemistry, and we'll talk about that on Friday. And also interstellar chemistry and other areas. That exactly the same sort of approach occurs. With interstellar chemistry, it's a little bit difficult to do this sort of experiment there. But nevertheless, they find ways of overcoming that problem. Okay, we'll break there. When we come back, if anybody has any questions, we can go through the questions then. But I think you all deserve a break. Okay, see you soon. So we'll be back at 10 o'clock.